Digital Logic live session, and today we're going to cover a number of topics that you guys already saw before. We'll cover them again briefly. You have used them to complete your second homework, which is already due, and so I'm going to cover this briefly. I'm going to go into some of the topics that we will see in the upcoming series. So last time we looked at Boolean algebra and also logic gates, so we'll do a little revision today, a couple of examples as well. So to get started, I'm going to start with DeMorgan's theorem. So again, today I'm going to share my screen. It says that A plus B with the bar on top of it is equal to A bar dot B bar. Also, the inverse is also true. A dot B all barred is equal to A bar plus B bar. Now last time we discussed that the plus represents the or relationship and the multiplication represents the and. And we also discussed that the bar on top of two terms represents an inverter on the output of that gate, and the bar across an individual term represents the inverter on the input. So let us draw the logic gate to represent this expression right here. Again, the plus represents OR, and again the symbol for the OR gate is this right here. So this represents the OR gate. Let's put two inputs here. The inputs are going to be A and B. Now the bar represents inverter on the end. Okay, the inverter is going to be the opposite of it. So if you write the logic is going to be A plus B, A or B, and then the inverter on top of it. And we are saying that this equals to an AND gate. So again, we have an AND gate here. The dot represents AND. We have an AND gate, and we see that A and B has the bar on top of them individually. So it means that the inverter is on the input. So we have A here and also B. So again, the output of this gate is going to be A bar ANDed with B bar. Right? Again, so you have A outside here. It goes through the inverter. After the inverter, what do we have? We have A bar. Right? B goes through the inverter. After the inverter, we have the opposite of B, which is B bar. And of course, they are ANDed together with the dot, and that's how you have your output right here. Likewise here, you have A ORed with B. So before the inverter right here, you actually have A plus B. After it goes through the inverter, it becomes inverted. Okay, so this symbol represents A plus B bar. This symbol represents A bar ANDed with B bar. Let's draw the second one. So again, this AND represents the dot represents an AND gate. So we start with a symbol for the AND gate. And again, the inputs are A and B, and the bar is on both of them, so it means that the inverter is on the output. So again, if you were to get the Boolean expression before the inverter, it would be AB, right? After the inverter is going to be AB bar, all barred, right? Likewise, we are saying that this equals to an OR gate. Again, plus represents OR, and we have two inputs here. One input is going to be A bar, second input B bar, right? So again here, the bar is on the input because the bar is on the individual terms. So the question is, are these two equal, right? We're saying that A plus B bar is equal to A bar times or ANDed with B bar. So the way you can test if they're equal, you need to draw the truth table for each of them and then determine if the truth table is the same. Right, so let's go ahead. We'll start by drawing the truth table for an AND and an OR gate. So let's draw the truth table for the AND gate, right? So for the AND gate, we said the truth table is going to be if we have A, B, and Y. We said for the AND logic, the output is only high when we have two ones. So when we have two ones, that's when our output is going to be high. Okay, I may have to scroll. right? Everything else would be 0. That's for the AND gate. What about the OR gate? For the OR gate, we said anytime we have a 1 on our input, we're going to have a high output. So we have no 1s here, so we have 0 here. But anytime we get a 1, we're going to have a high output. Either OR is going to cause this output to go high. And so we know that this is the logic for OR, right? So at this point here, let's draw the first gate first, which is going to be A plus B bar. So this is A plus B all bar. So this gate is going to be the same thing as the AND with an inverter on it, right? Sorry, the same thing as the OR with an inverter. So let's go ahead, and if we take Y bar here, so it's going to be the same truth table as the OR, but we have an inverted Y. So let's just write Y bar, right? So what would the opposite of 0 give us 1, opposite of 1, 0, 0, 0. So this is the output for A plus B bar. A or B, again the inverter is at the end of the OR. Okay, let's do the same, or let's draw the truth table for A bar ANDed with B bar now. All right, so again here, if we use this to represent A and B, then we can write A and B bar right here, right? So again here, we'll start with 1, 1. Let's just get the opposite here. So the opposite of B is going to be 0 here, and then 1 here, and 0 here. And the opposite of this one is going to be 1, 1, 0, 0, right? So again here, these two are ANDed together, right? We have A bar ANDed with B. Again, the AND relationship still stands. And what does the AND relationship say, or the AND logic says? Only when we have two 1s, we're going to have a high output, right? So in this case here, we have a high output here. And everything else is going to be low, right? All right, keep in mind that A bar is the opposite of A, and B bar is the opposite of B, right? So you can see from this two truth tables here that A or B all bar, here is the output here, we get 1, 0, 0, 0. If we then have the A bar ANDed with B bar, we get the same output for the truth table. So we can say that these two gates are equal, right, or equivalent. That's why, again, this is one way we can prove DeMorgan's theorem, that A plus B bar is equal to A bar ANDed with B bar, right? Now, of course, this can also work with multiple terms. If you have A plus B plus C, it's going to be the same thing over here, and we'll look at an example in a second. Let's go ahead and look at the second rule, right, which is going to be AB bar. So we're saying here that AB bar is equal to A bar OR with B bar, right? So again, if you draw them, and we drew them already, let's go ahead and draw the truth tables for them. These truth tables will, when we say the truth tables are equal, then that goes to prove that it's going to be equal, right? So let's start with the AND gate. A, B, Y, and then we'll do Y bar, because we know that AB is the AND gate of A and B. Okay, with the AND gate, you know the AND logic says that both inputs must be high for the output to be high. If we take the complement of this, which is the opposite, we're going to have 0 here, and we have 1s here, right? So A, B bar, the truth table is 1, 1, 1, 0, okay? Let's now do the truth table for A odd, A bar odd with B bar. So on here, I'm going to see, I need to erase this bar here. So I'll do the full truth table now with A, B, and then A bar and B bar. And then Y. So before I did not put A and B, I just put A bar and B bar. So I'm just going to put it here so you can see. All right, same as before, 0 0 0 1 1 0 1 1, and these are just all the possible combinations with our two variables. So A bar is the opposite of A, so we have here 1 1 0 0. B bar is the opposite of B, 1 0 1 0. And now for the logic here, the logic says it's either or. So we are doing or between A and B. So that means anytime we have a 1, our output will be high. So do we have a 1 here? Yes, high output. Do we have a 1 here? Yes, high output. Do we have a 1 here? Yes, high output. Do we have a 1 here? No, we don't. Low output. So you can see that this truth table for inputs A and B is the same as this truth table. So it tells you that these two logic expressions are equivalent. All right, so how do we use this? You will see that we use this to solve problems, right? And let's do an example right now. All right, so here's an example here where you're given a term A, B, C plus AD bar, right? So you're given this expression, you're told to simplify this, right? Simplify. Well, most times you simplify, you want to get rid of any terms that can be simplified, and especially you don't want to have a bar across two terms because you can use DeMorgan's theorem to break it down. So first, we treat this as one term here, and we treat this as one term, and we apply DeMorgan's theorem. So DeMorgan's theorem says that A plus B is going to give us A bar ANDed with B bar. So we apply it to these two terms right here. So we get that this is going to equal to, if we apply DeMorgan's theorem, we have ABC with a bar on top of it. We treat this as the A, ANDed with AD bar, and with a bar on top of it. Now you can see that we can apply DeMorgan's theorem to this one as well. And so when we do that, we end up with A plus B. So again, this is when we apply DeMorgan's theorem to this term here. And it's also ANDed with this guy here. We can apply DeMorgan's theorem to this term as well. We have A bar plus D bar bar. Now, of course, D bar bar is going to be D. Okay, so if we add this to here, you can see that we have A, and we have so this is going to be multiplied by this. This is our terms right here. So let's go ahead and multiply. We're going to have A bar plus A bar D plus B bar A bar plus B bar D plus C bar A bar plus C bar D. Right, so now we can cancel this too. So again, A bar times A bar is going to give us A bar. Right, and now we can factor out A bar from the rest. We will get D plus B. Now again, when you factor out A bar here, okay, so we will have B plus B. Then we also can factor out A bar from here as well, so we will get plus C bar. Okay, this should be, yeah, so this C bar, and this should be B bar, C bar. All right, now we have these two terms here, BD, B bar D, plus, all right, plus C bar D. Right, so if we decide to factor out, we can also factor out D from here. So we will have A bar D plus B bar plus C bar plus D B bar plus C. Right, so again, this we did by applying DeMorgan's theorem just across this, and so this is the term that we have brought it down to, right? So again, how do you prove DeMorgan's theorem? Like I said, you need to write the truth table for each of the expressions, and if the truth table is the same, then these two gates are the same. Okay, so again, DeMorgan's theorem, knowing DeMorgan's theorem, it brings us to a topic that we will consider called universal gates. So in this universal gates, we are able to use the NAND gate and the NOR gate to represent all the other gates. And one reason why this is important is because it is cheaper to manufacture NAND gates So it is very, since it's cheaper to manufacture NAND gates, some circuits use NAND logic. So NAND gates are used for inverters, for AND gates, and for OR gates, and so forth, right? So again, because it's cheaper to manufacture NAND gates, they are used for other gates. And you ask the question why, right? So let's look at the NAND gate. So NAND logic is the opposite of AND. So again, you can see let's draw the truth table for the NAND. Let's start with the truth table for the AND. Instead of putting Y, I'm just going to say AB, which is A and B. We already know that for AND gate, we are going to have a 1 on our output only when the two inputs are high. So this is the truth table for the AND. Let's do the NAND. Again, the NAND is the same as the AND with an inverter on the back. So that's why the bars across both here. And so it's going to be 1, 1, 1, 0. So this is the truth table for the NAND gate, right? This is the Boolean expression for the NAND as well. Okay. And again, we have said that according to DeMorgan's theorem, this is the same as A bar plus B bar, right? Which is the OR gate with inverted inputs, right? So let's see how you can use the NAND for how we can use the NAND as an inverter. The first thing we can see when we look at the truth table is that when we have two same inputs, the NAND behaves as an inverter, right? So if you have two ones, your output is 0. If you have two zeros, your output is 1. So the NAND behaves as an inverter if we connect the two inputs together. So here we go. This is the NAND behaving as an inverter right there. Again, this is the symbol for the AND with a bubble at the back of it. This is the NAND. And so if this is A here, we are going to get A bar on the output, right? Alright, so this is the NAND behaving as an inverter, and we can see that in the truth table. We have two ones on the input, we have 0 on the output. We have two zeros on the input, we have 1 on the output. So the NAND can be used as an inverter, right? The second thing the NAND can be used as is, you guessed it, an AND, right? Because if you have an AND, we say that the NAND is the AND gate with an inverter on the back. Guess what? If you put an inverter after the inverter, you're going to get back your original value. So let's start with the NAND gate. So this is an AND here, A and B. So what do you get after the NAND? You get A and B, all barred, so it's inverted. Now if you run this through an inverter, which is going to be another NAND, we said if you connect the two inputs for the NAND together, it forms an inverter. We said whatever comes in, so what is coming in here is A dot B bar. Whatever's coming out here is going to be A dot B. Right, so again, this is the AND, so you can see how we can use the NAND to form an AND gate, right? So if you have a NAND, if you have two NANDs, right, you can connect the two inputs of one together to form an AND, and then you can also place it after the NAND, and it's going to invert the output, so you have the AND logic here. Okay. The next thing we can talk about is the OR gate. So we can use the NAND to form an OR gate. Keep in mind that the NAND, we can write the NAND because of DeMorgan's theorem. We can write the NAND gate as a OR gate with inverted inputs, right? So again, we say a NAND gate is the same as a OR gate with inverted inputs. But guess what? Since we have, we can use the NAND as an inverter, we can simply place the inverter on the inputs of this gate here. So A is going to be A, B is going to be B, and then we're going to have the OR logic. So this is what I'm talking about. So we have a NAND gate here, and on the inputs we're going to put inverters. And so the inverter is where we connect when we connect the inputs of the NAND gate together. Alright, so this is going to be A, and this is B. So after A, when it goes through the inverter right here, we have A bar, correct? When B goes through the inverter, we have B bar. When they go through the NAND gate, what do we have? We're going to have A bar, and that with what? B bar, yes? And it's all bar. Does that make sense? So we have A, it turns to A bar, B turns to B bar. Right, so this is what we get for the NAND gate. But keep in mind, we said that because of DeMorgan's theorem, we can write this NAND gate as an OR gate with inverted input. So we just put an inverter on A and B. So we essentially have an OR gate which is A plus B. So let's just resolve this, right? Let's apply DeMorgan's theorem to this. What do we have? Applying DeMorgan's theorem to this, right? This is going to be an individual term. This is going to be an individual term. We're going to have A bar plus B bar. And why do I say that? Again, when we began, we saw that A dot B bar is equal to A bar plus B bar, right? So this is the same thing we're applying right here. We're saying here that A bar dot B bar, all bar, is going to be A bar plus B bar, right? Now again, A bar is the same as A, so we get here A plus B, which is an OR gate, right? Okay, so again, this is the NAND gate acting as a universal gate. Now we can do the same thing for the NOR gate, which can also act as a universal gate because of DeMorgan's theorem as well. So let's do the same thing for the NOR. Now notice I did not go into the exclusive OR. I'm going to show you in a second. So let's do the NOR gate. So here's the NOR gate. It's the same as the OR with inverted inputs. So you have A and B here, and you have your output is going to be A plus B all bar, right? According to DeMorgan's theorem, this is the same as A bar and that with B bar, right? Okay, so first thing we can do, let's draw the truth table for the NOR gate. We will see that the truth table is going to be A, B, A plus B. Okay, NOR gate, right? Truth table here, our combination 0, 0, and 0, 1, and 1, 0. Again, we're just counting in binary 0, 1, 2, 0, 1, 2, and 3, right? That's the maximum we can do. So again, here, according to the OR gate, so let me do the OR first. According to the OR gate here, anytime we have a 1, we're going to have anytime we have a 1 on the input, we have a 1 on the output. So again, this is the output for the OR gate, right? When you have the NOR, we simply put a bar on top of it. So the output is just going to be inverted, right? So again, being inverted, we're going to have 1, 0, 0, 0, right? Okay. So if you look at the truth table, we can see again that if the inputs are connected together, so if you have 1 on the input, if you have 1 on both inputs, you have the opposite on the output. If you have 0 on both inputs, you have the opposite on the output. And so we can see that the NOR gate can be used as an inverter as well, right? So if we connect the inputs together, and we put A on here, the output is going to be A bar, right? And we can see that from the truth table. 2 1s gives us a 0. 2 0 gives us a 1. So we'll call that inverter. An inverter is the same as a NOT gate, in case you come across it. All right, next we're going to look at the OR, you guessed it. If we have the NOR gate right there with inputs A and B, and we have output here A plus B bar, and we connect that to another NOR gate which is behaving as an inverter, then we are going to have an OR. Right, so again the output here is going to be A plus B, which is the OR. What about the AND gate? Well, it's going to be very similar to the other one. If you remember, we said that the NOR gate is equal to the AND gate with inverted inputs. So we have an AND gate already, we just need the inverters. We need to get the opposite of the input, so we can have a NOR gate with inverted input. So again here we have a NOR gate. Okay, let me bring it a little closer. Let's put a NOR gate right there. All right, so we need inverters on the inputs. My NOR gates don't look very pretty, but if you have it where it's legible, okay, I'm even going on the side. All right, so let's look at the logic. You go for an inverter, A becomes A bar, correct? B becomes B bar. You go for the NOR gate, A bar becomes A bar plus B bar, all barred, right? Now let's apply DeMorgan's theorem to this. What do we get? We're going to see, treat this as a term, treat this as a term, and the bar on top of it, we're going to have A bar bar and that with B bar bar. Again, A bar bar will be equal to A, so this is A, and with B, so this is the AND gate. All right, so again, this is why we call them universal gates, because we can use the gate to come up with the other logic, like the AND, which is the basic, the AND, the OR, the NOT, right? Let's talk about the exclusive OR gate that we discussed some time ago, right? So for example, the exclusive OR, this was the symbol for it, and we said that the logic was a bit different in that we said that the Boolean expression was A or B. Now if you look at the truth table, all right, let's just put Y here to represent it. Okay, I'm going to have to write straight. All right, so if you look at the logic we said here, when the inputs were the same, we had a high output, right? That was the what we had for the truth table. Now I also gave you another expression for the exclusive OR. The exclusive OR is actually a combination of AND and OR gates, right? So let's here is the expression. The expression is A bar B plus AB bar, right? So let us go ahead and draw the circuit for this, and let us write the truth table for it to show that the expression of this is the same as the expression right here. So to show that they are equivalent, right? So how do you draw this? Again, you know that this is an AND gate because it's multiplied, and you know that there's an inverter on the A. So let's go ahead and draw an AND gate here and put a bubble on A. Right, so this is going to be A, so A bar coming in, and this is B, so the output here is going to be A bar B. Likewise, we have another AND gate here, and of course the inverter is on B this time. So instead of drawing A and B, I'm just going to connect it right here. Make sure we have a connection right there. So the output here is A, B bar. Now they are all together because the plus represents all, and so we can draw an OR gate and connect them to the OR gate as the inputs. Now the output here is going to be A bar B plus A B bar, right? Let's do the truth table to ensure that we have the correct answer right here, right? So we can do a truth table with A, B, and then we can do one for A bar B, and we can do another column for AB bar, and then we can do a column for the last one where they are added together, A bar B plus AB bar. Right, just to show that the truth table is going to be equal. Right, so again here we have 0, 0, 0, 1, 1, 0, 1, 1. Okay, what is the, if we have A, the opposite of A and B ANDed together, what is going to be the output? Now keep in mind, for us to have a high output of AND, both inputs need to be 1. Now how will A bar become 1? It's simple. When A is equal to 0, A bar is going to be equal to 1. So we are looking for when we have A bar being 1 and B being 1. So again, when A is 0, A bar is 1. Is B 1? No. When A is 0, A bar is 1. Yes? Now is B 1. So we are saying A bar is 1 here. A is 0, A bar is 1. B is 1, so we have a 1 right here. We have a 0 there. Then we're asking the question, when A is 1, A bar is 0. So we cannot have a high here. What about here? When A is 0, when A is 1, A bar is 0. So again, the AND gate only has one time it's going to become, there's only one time it's going to have a high output, and that is when both inputs are true. And both inputs are true right here. Why? Because B is 1, and we want to AND it with A bar, and A bar is going to be 1 when A is 0. Okay, because it's the inverse of A. Let's look at this one here. Again, we are ANDing A and B bar. Okay, so A 0 here, B bar. So again, B bar is going to be equal to 1 when B is 0. Okay, so A 0, B is 0, so B bar is 1. So we have 0, 1. The AND gate says we need 1, 1. What about here? A 0 and B is 1. So if B is 1, B bar is 0. So 2 zeros, still 0. What about here? A is 1 and B bar is 0. Now keep in mind, sorry, when B is 0, B bar is 1. So this is where we have 1 for A, and we have 0 for B, which is going to be 1 for B bar. So we have a 1 right here. And again here, A is 1, B is 1. If B is 1, then B bar is 0. So we have a 0 for here. So now this is going to be the OR. Right, we're gonna do all logic on these two inputs right here. Now OR means anytime we have a 1 in the input, the output is 1. So do we have a 1 here? No. Okay, 0. Do we have a 1 here? Yes. Okay, we have a 1. Do we have a 1 here? Yes. Do we have a 1 here? No. Right, so this, you can see that breaking down the logic and getting the truth table is the same as we had initially, right? So let's go ahead and do it for let's apply DeMorgan's theorem to this expression so we can get the exclusive NOR gate. Now keep in mind the exclusive OR, the output is going to be the opposite of the exclusive, sorry, the exclusive NOR's output is going to be the opposite of OR. So let's go ahead and do that. So for the exclusive OR, EX NOR. So it's going to be the same thing as the exclusive OR. Okay, let me erase that. So the exclusive NOR is the same thing as the OR, but just with an inverter. So you expect that the truth table is going to be AB, Y, so instead of having a 1 here, we're going to have a 0 here. Oh, I'm sorry, it's the opposite. So when we have two of the same inputs, our output is going to be high. And when we have different inputs, our output is going to be low. Same way we up here. So this was incorrect. This is the opposite here. Apologize for that. This should be 0, 1. So when we have different inputs, then the output is high. So let's apply DeMorgan's theorem on this here. So again, we're saying, the question we're asking, is this the same as here's the expression for the exclusive OR. It was A bar B plus AB bar. Right? Now, this is for the exclusive OR. If we put a bar across this and we simplify it, it should turn to the exclusive NOR, right? So let's go ahead and work that out. So we're going to apply DeMorgan's theorem to this, and this is what we get, right? So we treat this as one term, and we treat this as one term. So we have here A bar B bad. Okay, let's just go a little higher. A bar B bad plus, okay, not plus, but ANDed so we're going to AND this with A B bar all bad, right? Now you can see that we need to apply DeMorgan's theorem again. So applying it again for this term by itself, we end up with A bar bar plus B, right, times A the A bar plus B bar bar. Right? Now we need to expand this, so we're going to have, again, A bar bar is going to be A. So we have here alright, let's just verify this. Again, this is going to be A bar bar plus B bar, and this is going to be A bar plus B bar bar, right? So again, now A bar bar is going to be A, B bar bar is going to be B. So now we have A times A bar. Now again, based on the rules of DeMorgan's theorem, anytime you have A times A bar, that will go to 0, right? Because you will never have a condition where A is going to be, where both A and A bar are going to be 1 because they're opposite. Plus, so now we're going to do A times B. So we're going to have AB. Then we're going to do B bar times A bar. So we have A bar B bar. Likewise, we're going to have B bar times B, which will go to 0 as well. So your answer is going to be AB plus A bar B bar. Now the question is, if we do the truth table for this expression right here, is it going to result in this truth table right here? That's how we know that they're equivalent, and it will. So let's go ahead and write the truth table for it. We'll just do an extended truth table. So we'll do AB, then we will do AB and A bar B bar. Then we will have the answer here, which is AB plus A bar B bar. All right, let's go ahead. So again, we'll start with 0, 0, 0, 1, 1, 0, 1, 1. So again, for the AND gate, we're only going to have a high when when all the inputs are high. What about here with A bar B bar, right? Now keep in mind, if A bar is the opposite of A, so we're only going to have a high when A is 0 and B is 0, which is only this condition right here. And all the others are going to be 0. So when you have A bar and A and B, A bar is 0, B bar is 0, so we have a 0 here. When we have A being 1 and B bar being A being 1 and B being 0, it means that A bar is 0 and B is 1, so we have a 0 here as well. Likewise, when A is 0 A bar is 1. And when B is 1, B bar is 0. So we have a 0 here as well. Okay. So now, here we are just ORing these together. OR means anytime we have a 1 in these two, again, these are the two inputs, our output is going to be 1. So the question is, do we have a 1 here? Yes. Do we have a 1 here? No. Do we have a 1 here? No. Do we have a 1 here? Yes. So you can see that the truth table here for this Boolean expression is the same as the truth table for our exclusive NOR gate. And so they are the same. They are equivalent. Now this NOR gate, you can see, is used a lot of times as a comparator, because it can compare two inputs. When the inputs are the same, it's going to have a high output. All right, let's talk about simplification, right? Again, in your lecture notes, you had the different rules for Boolean algebra that you can use for simplification, with some examples as well. Before we go on and we continue, let's look at briefly some expressions to gates and gates to expression. I think we started doing this already. It's not difficult to do, as long as we can understand what the plus means and what the multiplication means. We should be fine, right? So I'll put here expressions to gates. Okay, so what does this mean? Again, we need to know that the plus represents OR, and we need to know that the multiplication represents AND. What does that mean? So if you see A bar B C plus A C, then you know that, okay, we have this represents an AND gate with two inputs A and C. This represents an AND gate with three inputs A bar B and C. This represents an OR. So it's easy to draw this. You start with the AND gates first. Okay, you can say, okay, this is A, so then A bar is inside of the gate. This is B, this is C, and you can draw the other AND gate. This is going to be A and C. And then how are they connected? With an OR. The plus represents OR, so you connect the inputs to the OR. Right, you can write the output expression here, A bar BC. You can write the expression here as well, AC. And then you write the expression that comes out, A bar BC ORed with AC. Right? So as long as you understand, hey, this is what this represents, and this is what this represents, you can go forward and backwards. Let's do an example of, so we did the expression to the gate. What about the gate to expression? So if you're given a circuit, it can be very complex or not. Right, notice here I don't have an exclusive ORs here. That's just all right, let's go ahead. All right, so let's say that this is A, this is B, this is C, this is D, this is A, B, C, D. All right, two inputs here. What's the output here? It's going to be A. It's going to be A times B, which is A and B, right? What about the output here? We have four inputs. We have A ANDed with B, ANDed with C bar, ANDed with D. What about here? The input going in here. So this is the AND gate. What are the inputs for the AND gate? The input is going to be D times ABCD. Okay, I'll just stop writing on the side. Again, based on simplifications, if you have two of the same number, it equals the same. So you have here A. See how I can. So we have here A, B, C bar D, right? That's what it equals to. What about here? The output here is going to be A, B, ORed with C. And so the output of this gate is going to be AB, ORed with C. And it's AND gate, so it's multiplied by something, and that's going to be this right here. AB C bar D. Right, now if we wanted to simplify this, we can. So let's just work on it right here. Okay, so we have here, if we factor out AB, we're going to have AB, and we're going to have C bar D. Oh, I started wrong. Let's start again. So if we do AB on the outside, we're going to have 1 plus C bar D plus C. Right? 1 plus anything is the same as or in 1 with anything else. It will go to 1. So we end up with AB plus C. That's the simplified result for this expression up here. So the basic building blocks, AND gates and NOR gates and OR gate, they allow us to build more complex circuits, right? So AND gates and OR gates are simply building blocks that we will use for more complex circuits. So what are some of those complex circuits that we want to discuss, that we will discuss in the class? Just have a list right here. So we'll talk now about combinational circuits. So we want to discuss adders, subtractors, decoders, encoders, multiplexers, and demultiplexers, and of course we have counters, and we have timers, frequency dividers as well. Following that, we also have arithmetic logic units. So we want to use logic gates to build this combinational circuits, and of course we have a number of examples that we will share with you. Now before you guys go further, I have a project that I want you to work on. This project involves, switch out to my, so this project involves using logic gates to build a simple application. Like I mentioned, this class is not difficult. We have lots of opportunities to practice. So we'll be working with a circuit diagram. We'll be building a circuit, and also not only building the circuit on breadboards, but we'll also be designing a PCB for that circuit as well. It will involve a timer, some switches, a couple AND gates as well. So look out for the documentation. I'm going to post it very soon. Again, this has brought us to the end. I'm going to pause right there before I start the second session. All right, you guys, peace.